Hello, and welcome to this explainer. If you're a college student deep into your engineering or chemistry studies, or really just someone trying to make sense of the rapidly changing world around us, take a deep breath and settle in. Today, we're not going to be staring at a whiteboard full of overwhelming complex equations. Instead, we're going to explore a quiet, honestly almost invisible kind of magic that is completely reshaping how we move. We are going to look at the elegant chemistry happening right inside an electric vehicle. So I want you to imagine a crisp, quiet morning commute. You're sitting inside an EV, just gliding down the highway. The ride is incredibly smooth, and aside from the gentle hum of the tires against the pavement, there is absolute silence, right? There are no tiny explosions happening under the hood, no heavy pistons pumping up and down, no exhaust fumes. It's a profound shift from over a century of traditional driving. So it kind of makes you wonder, how exactly does a 2-ton machine propel itself forward with such effortless, quiet grace? Well, the secret doesn't lie in brute mechanical force. It's actually all about a closed, beautifully elegant system of chemical energy. You see, the traditional internal combustion engine relies heavily on consumption, burning fuel and expelling waste just to create movement. An electric vehicle, on the other hand, relies entirely on the highly efficient properties of lithium. It's literally the lightest metal on Earth, yet it holds the key to moving a massive, heavy car. Instead of a cycle of consumption and destruction, it creates this amazing system of preservation and energy transfer. Okay, let's dive into the microscopic landscape where all this actually happens. Let's look at the anatomy of a lithium-ion battery cell. On one side, we have the positive electrode, the cathode, which is typically made of layers of a lithium metal oxide, like lithium cobalt oxide. Then, on the other side is the negative electrode, the anode, made from layers of porous carbon, usually graphite. And separating them is a polymer gel electrolyte and a porous separator. It's this incredibly peaceful, self-contained environment designed for one very specific purpose: the smooth, uninterrupted transit of lithium ions. A great way to think about these lithium ions is like tiny, super diligent commuters. When you plug your car in at night, you're providing external electrical energy, right? And this energy prompts our commuters, the positively charged lithium ions, to leave their home in the cathode, travel across that polymer gel, and tuck themselves neatly into the layers of the graphite anode. This is the charging mechanism. They're just resting there, storing up all this potential energy. Then, when you press the accelerator the next morning to head to class, the discharging mechanism kicks in. The ions naturally want to go back home to the positive electrode. As they flow back, electrons are forced to take a detour through the external circuit, and that detour is exactly what provides the electrical current to spin the car's motor. And this brilliantly illustrates the sheer elegance of the whole system. It is just a continuous, harmonious loop. Step 1. The ions move to the anode during charging. Step 2, they store massive amounts of potential energy. Step 3, they return to the cathode during discharge. And finally, Step 4, that return trip is what actually powers your vehicle. There's no friction of metal on metal, no combustion, no burning. It's just a quiet, microscopic commute happening millions of times over, instantly translating chemical potential into forward momentum. So moving into our first main section, powering the drive, from microscopic ions to macro performance. We've seen the serene dance of the ions on a microscopic level, but let's zoom out for a second. How does this tiny, silent reaction translate into the very real, macro experience of driving a heavy EV down a highway? Well, because lithium is such a lightweight metal, we can pack massive amounts of energy into a really compact space. That is the fundamental difference between a battery dying on a quick 5-minute trip to the campus dining hall and having the range extension to drive hundreds of miles all the way home for the holidays on a single, peaceful charge.
But an EV isn't just some slow, overly practical commuter car. They're honestly incredibly thrilling to drive. Despite the calm chemistry happening inside, these batteries deliver instant performance. Because the system doesn't have to wait for liquid fuel to pump, mix with air, ignite, and then push a heavy piston, the lithium-ion battery can rapidly discharge large amounts of energy the exact millisecond your foot touches the pedal. This delivers incredibly quick, seamless acceleration and effortlessly maintains high speeds, all while keeping that characteristic serene silence.
Now, what's truly fascinating is how the system handles slowing down. In a traditional gas car, when you hit the brakes, all that forward momentum, your kinetic energy, is essentially just wasted as heat through friction on the brake pads. But an EV uses what's called regenerative braking. The electric motor essentially runs in reverse, acting as a generator. It captures that kinetic energy and converts it back into electrical energy, sending those lithium ions straight back to the anode to be stored again. You are literally recharging your car just by slowing down. It is the ultimate expression of efficiency. And this incredible efficiency extends to all the comforts you enjoy inside the cabin, too. The lithium-ion battery quietly acts as an auxiliary power hub. It runs your air conditioning, those heavy-duty infotainment screens. And, yes, it seamlessly charges your phone and laptop while you drive, all without heavily draining the primary propulsion system. In plug-in hybrid vehicles, it handles the start-stop systems, instantly and quietly restarting the combustion engine whenever it's needed. It just manages the entire environment of the car with total calm reliability.
Which brings us to part 2, a harmonious loop. Giving back. Beyond the vehicle. Up to this point, we've really only looked at how the battery takes energy from the wall to power your journey. But the tech is actually shifting from a one-way street to a two-way harmonious loop. Your electric vehicle isn't just a mode of transportation anymore. It's becoming a mobile energy storage unit. This is what we call vehicle-to-grid, or V2G technology. Imagine a crazy hot September afternoon when everyone back at the dorms is absolutely blasting their AC, heavily straining the campus power grid. If your car is parked and plugged in, it can smartly send some of its stored lithium-ion energy back to the grid, helping to stabilize the network for everyone. And then it simply charges back up later when demand drops. As this quote perfectly summarizes, EVs aren't just taking energy, they are giving back to stabilize the grid. It's a really beautiful, cooperative concept. So as you close your laptop or finish up your notes for the day, I hope you take away this one simple realization. The technology powering our future isn't about loud brute force anymore. It's about balance. The next time you see an electric vehicle silently gliding past you, remember the millions of tiny lithium ions quietly commuting back and forth inside it, a true masterpiece of invisible engineering. But it leaves us with a pretty fascinating question to ponder. If our vehicles are no longer just cars, but essentially mobile power plants, how is that going to change the way we build our cities and our lives tomorrow? Thanks so much for learning with me today.